Good morning. In this video, we are going to find the moment of inertia by using integration method. Now let us go to the problem. Find the moment of inertia of the following section with respect to centroidal axis. Now this is the given composite section. There are 3 points A, B and C. A is located at the origin, B is located at 1, 3 and C is located at 2, 4. There is a straight line between the points A and B, and also there is a straight line between the point B and C, but there is a curve between the points A and C. Now let us divide this section into small sections. For that I am going to draw a line through the point B in vertical direction. Now there is a straight line, a vertical line is drawn from the point B. Now it divides this composite section into two sections. So this is the first one and this is the second one. Now this is the centroid for this object and this is the centroidal y-axis. We have to find the moment of inertia with respect to this axis only. So this is what here it is done. This is section 1 and this is a straight line, whereas this is a curve. Similarly, this is section 2. Here is a straight line and here you have the curve. Now let us go to the second step. Now before going to the second step, we have to know one more important point. If you look at these two sections, they are not in regular shapes like square or rectangle, etc., etc. So there is no direct formula for finding the moment of inertia. So we have to go for integration. So this is an important point to note. When we are unable to get the direct formula for any section, we need to go for integration. Moreover, the requirement is to find the area moment of inertia with respect to centroidal y-axis only. So I am going to choose the variable related to y-axis only. Here I am going to choose the variable a1 and then x1, IO, y1 only. You may get a confusion. Earlier this variable is related to centroidal axis, but since I am going to use integration, I am going to choose the base axis only. Okay, keep this in your mind. Now let us go to the first section. So here is the first section and this is the position of G1. Now we have to find this area A1 and X1, then moment of inertia with respect to this axis. Okay, I O y1. Okay, so a1, x1 and y1 we are going to find. Now you see here there is a curve which is the equation is y equal to x square, whereas here there is a straight line. So we have to find the equation for that. So this is the formula: y minus y1 divided by y2 minus y1 equal to x minus x1 divided by x2 minus x1. Now we need to have the variables for this. So I am going to take these two, a. Now this is x1 y1 and this is x2 y2. Substitute the values, you will get the answer as y equal to 3x. Now first variable is a1 equal to integration of dA. Now I need to find the dA. For that I am going to choose a small elemental area like this, and which is being located by x distance from y axis. Now the dimensions are the width is equal to dx and the height is equal to y. Now you see here both x and y are variables here, because I can adjust this position of this dA. If I adjust the position of this dA, according to that the variables x and y will vary. So now these two are the variables, and this is a rectangle. Now since it is a rectangle, this can be the area can be calculated as y into dx. Okay, y into dx, and moreover dx because it is parallel to x axis. Now y, as I said, it is a variable. Now you see here this is the bottom end of that dA, where the equation is y equal to x square, and this is the top end of that dA, where the equation is y equal to 3x. Now y can be written as y2, the difference between these two, y2 minus y1. Now y2 is nothing but the upper limit where y equal to 3x, and y1 is nothing but the lower limit where y equal to x square. and substitute the upper and lower equations. So this will become like 3x minus x square into dx. Then second important thing is the limits. You see here, this is the lower limit where x equal to 0, and here is the upper limit where the x will become 1. Okay, so the one is referred from this one. So this is the upper limit where the x equal to 1, here the lower limit where the x equal to 0. Now the dx will become like 3x minus x square into dx, and here is the limit 0 to 1. Integrate and substitute the values. Finally the a1 will become like 1.16. The next variable is x1, and this is the equation integration of x dA divided by integration of dA. We already found the answer for this one. Integration of dA is nothing but a1. So we have to find the value for the numerator. Now this is the numerator, integration of x dA. Now we already know that dA is nothing but 3x minus x square into dx, and the limits are also 0 to 1, and just multiply this x inside the bracket. So the equation will become like 3x square minus x cube into dx, and here is the limit 0 to 1. Integrate and substitute the values. Finally the integration of x dA will become like 3 by 4. Now substitute this one into this equation, and you will get the answer as x1 equal to 0.64. Now the next one is the moment of inertia with respect to base y axis I O y 1, which is equal to integration of x square dA. Now again we have to go for the term called dA. So here is the dA again, 3x minus x square into dx, and the limits also same, 0 to 1. Now substitute here and integrate the values. Finally you will get the answer as 0.55. So that's all about the section 1. Next I am going to take the second section. Here is the point B to C and this portion, and I am going to draw a separate diagram for it. Now this is the separate diagram for the second section G2. Now we need to find the A2, X2 and the area moment of inertia with respect to this base axis. Again you see here there is a equation between the points B and C. So first we have to find the line equation. So there is a line between the points B and C. So we have to find the equation for that one. Again this is the equation of line y minus y1 divided by y2 minus y1 equal to x minus x1 divided by x2 minus x1. So the values are, this is x1, y1, here it is x2 and y2. Substitute all the values. Finally we will get the equation as y equal to x plus 3. Now the first variable is the area of the second section. For that I am going to use integration equation. So integration of dA. Now I need to know the answer for the dA. Now this is the small element dA, which is being located by x distance from y axis, and the dimensions are, the width is again dx because it is parallel to x axis, and the height is y. Okay, here again x and y are variable. This the variables will change according to the position of this small element. Okay, if we move over here, accordingly these two will have different value. So these two are now variables. And if you look again, here is the curve which is equal to, where the equation is y equal to x square. Here is a straight line where the equation is y equal to x plus 3. Now the formula for dA is y into dx. Okay. Now as I told earlier, y is a variable, so it can be written as y2 minus y3 into dx. Now y2 is the equation of the upper line, which is y equal to x plus 3, and y1 is the bottom one where y equal to x square. Now substitute the values and rearrange, you will get something like this. Again here the limit, if you look at the limit, so the x varies. Here is the lower limit 1 and the upper limit is 2. Okay, this comes from this one. You see, if you see here the x equal to 1, and for the upper limit x equal to 2. So the limit varies from 1 to 2. Now substitute dA, and here is the limit 1 to 2. and integrate the equation and substitute the upper limit and lower limit. Finally, you will get the answer for a2 is equal to 2.16. The next variable is x2. x2 is nothing but integration of x dA divided by integration of dA. We know that integration of dA is nothing but a2. Now I have to get the answer for the numerator, integration of x dA, and I know that dA is nothing but x plus 3 minus x square dx. It comes from this one. So this is the answer for dA. Okay. Then multiply this x inside, so finally it will be something like this, and the equation and the limit is 1 to 2. Now integrate this equation and substitute this upper limit and lower limit. Finally you will get the answer for x dA is equal to 3.07. Now x2 is equal to integration of x dA divided by a2. Substitute the values. Finally, we will get the answer for x2 equal to 1.42. Similarly, for the moment of inertia with respect to base y axis, nothing but integration of x square dA, and for dA again get the same, that is x plus 3 minus x square into dx, and the limit changes from 1 to 2, and substitute and just multiply x square into the bracket. So this equation will now become like this, and now integrate it and substitute the upper limit and lower limit. Finally, you will get the answer as 4.55. Now in the given problem, it is given that we have to find the area moment of inertia with respect to centroidal y axis. So we have to find the position of the centroid from the base axis, but here it is given as only y axis, so it is enough to find the x bar only. So here is the formula for x bar: x1 a1 plus x2 a2 divided by a1 plus a2. Substitute all the values, and finally you will get the answer is 1.147. Now what I am going to do is, first I am going to find the moment of inertia with respect to this base axis. Then using parallel axis theorem, I am going to find the area moment of inertia with respect to this centroidal axis. So here is that one, IOA, which is nothing but moment of inertia with respect to base axis, which is equal to IO y1 plus IO y2. Substitute the values, finally get the answer as 5.1. Now the next one is moment of inertia about the centroidal y axis. Further I am going for parallel axis theorem, and it is equal to IOY, which is nothing but moment of inertia about base y axis, and this is the moment of inertia about centroidal y axis plus A into d square. I want to know this only, so I am going to take that in the left hand side. So this equation now will become like this. Here A is nothing but area of the composite section, and d is the distance between base y axis and centroidal y axis. So now A equal to A1 plus A2, so the answer is 3.32, and D, which is nothing but distance between OY and GY, which is equal to again x bar, which is equal to 1.147. Substitute the values, finally you will get the answer as IGY equal to 0.72. So this video is little bit longer, but it gives a clear cut answer for finding the moment of inertia of a irregular shapes by using integration. Thanks. We will meet in the next video.